Okay, welcome to Lab Workshop 3 Part 2. So the second problem that we'll do in this workshop is called Southern General Hospital. So the hospital board has approved a minor expansion of not more than 10 beds at a maximum cost of $210,000. Beds are needed in the maternity ward and the cardiac ward. The board has insisted that at least 2 of the new beds be placed in the maternity ward. So maybe that was a directed donation of some sort. So the table that you've been given shows the profit and constraint coefficients. So we're told that a maternity bed gives us $20 profit a day, a cardiac bed gives us $25 profit a day, a maternity bed costs $20,000 and a cardiac bed costs $24,600. And we're asked to determine how many beds should be added in each ward using linear programming. So we know that we have to set up, the first section that we would set up here is our model parameters. We're asked how many beds should be added in each ward. So we're going to have the problem we're trying to solve here. Our decision is how many maternity beds do we add and how many cardiac beds do we add. So I will call the first column here maternity, the second one cardiac. And the model parameters is where we put all the data we've been given. Generally, the first thing you want here is the coefficients for your objective function. So what is our objective here? And it's might be a little confusing because we've been given both profit and cost values for each type of bed. But if we think about, are we trying to maximize profit or minimize cost? If we were actually trying to minimize cost, we wouldn't add any beds at all. So we're probably trying to maximize profit. This is a U.S. hospital. So we will assume that we're trying to maximize profit. So my profit coefficients are in terms of dollars per bed per day. And I'm told that maternity beds make me $20 and cardiac beds make me $25 a day. And now we want to list our constraints. So the first constraint says the hospital board has approved a minor expansion of no more than 10 beds. So we have a maximum number of beds. We need limits for our constraint. So the limit here is 10 beds. And then I need the left-hand side of my constraint coefficient is a linear function of my decision variables. So what I really want to say is that the number of maternity beds I add and the number of cardiac beds I add have to be less than or equal to 10. So my coefficients here are just 1 and 1. The second constraint I have is maximum cost of $210,000. So this is a budget constraint. So maximum cost. My limit is $210,000. And my total cost is going to be $20,000 times the number of maternity beds I add, and then $24,600 times the number of cardiac beds that I add. So this is maximum total cost. The third constraint that we have is that at least 2 of the new beds must be placed in the maternity ward. So how we would express that is we want to say that the decision variable for maternity beds has to be greater than or equal to 2. So it's going to have 1 here. My limit is 2. And we aren't really talking about cardiac beds at all, so it will have a coefficient of 0. So that's a minimum number of maternity beds. In the middle of my spreadsheet, I set up my decision variables. So I will call the number of maternity beds XM. I will call the number of cardiac beds XC. But it's the cells underneath those labels that I'm interested in. That's where my values are going to show up. And then model output is the final section of my spreadsheet, and my columns here are value, right hand side, and slack/surplus. And the very first thing I want is my objective function. So here's where I put my mathematical expression of the objective function. So that is a sum product of my profit coefficients and my decision variables. That's going to end up being my total profit. I want to maximize my total profit, which is equal to a sum product of these profit coefficients, comma, and the cells where my decision variables will appear. Now I do want to make that absolute reference for the decision variables, because I'm going to then be able to copy this function down to the other cells. So now I want to put my constraints, so I'll just copy the labels for my constraints from up here down here. So the maximum number of beds, this is just is equal to a sum product of the coefficients here, comma, and my decision variables. But I really can just, instead of doing that, I can just copy my objective function. As we saw in the previous example, I can copy that function down, and so long as I have kept everything in the same order, I'll get the correct sum products for each of my constraints. On my right hand side, that I'm just going to point to my limits. So right hand side for the first constraint is there, and then I can copy with relative references, I can copy that down. And then slack surplus is equal to the difference between the right hand side and the value. So I just subtract those two cells. So now I should be all set to use Solver. So I go to the Data tab, I get Solver, I show it where my objective function is, so I want to set that objective to, in this case I do want a maximum, so I'll leave the maximum button checked. By changing, I show it where my changing cells are, and then I've got something left in here. I will reset. Okay, I'll start over again because I had that from a previous attempt. So I'm going to set my objective. I point to the objective to a maximum by changing these variable cells. Now I can add my constraints. And there is one trick as far as adding constraints. If I have maximum constraints and minimum constraints grouped, I can add more than one constraint at once. So here I have two maximum constraints. So I can show it both left-hand side, the cells where both left-hand sides are for those constraints. So the value there has to be less than or equal to the right-hand side. So I show it where both of those right-hand side constraints are. And then I'm going to add my last constraint. So this is the left-hand side. That must be greater than or equal to, this is the right-hand side. When I'm finished adding constraints, I say OK. So I can see up here that I've actually got two constraints in with the one command there. It's a good idea to just sort of check the row numbers, make sure that you have selected the right rows. I've got my checkbox for my non-negative constraints. I'm selecting a solving method of simplex LP, and I say solve. So it tells me that solver found a solution. My constraints are satisfied. And I look at my solution, and it tells me that I should add 2 maternity beds and 6.9 cardiac beds. And when we discussed linear programming, we said one of the assumptions with linear programming is that our decision variables are continuous variables. In other words, I can add 6.9 beds, but I can't really in this case. A lot of times in manufacturing, yes, I can make half of a computer or half of a chair one day, and then I can come in the next day and finish up the other half. But I can't add 6.9 of a bed. So I could just round that down and say, okay, I'll add 2 maternity beds and just 6 cardiac beds. But I really am sort of, but there might be a better solution. And so I'll show you something that we can do. And this is part B of the question. It says, add additional constraints to ensure that the number of beds added in each ward is an integer value. So I can force my decision variables to be integers. To do that, I want to return to the solver parameters dialog. So I'll check this box here, say OK. And I'm back here. I want to add another constraint. So here, I'm going to say that my decision variables have to be integers. So I'm going to point to the 2 cells where my decision variable solution goes. I'm going to say those 2 cells. In the middle here, I have some choices here. I can say int means integer. So those 2 cells have to be integers. I'll say OK. So I can see I've added that constraint at the top of the list there. And I'll say solve. And it found a solution. So it's telling me that it's only going to add 6 cardiac beds, but by doing that, it actually saved enough money to add a 3rd maternity bed. You'll notice that the objective function here actually has the profit has gone down with 2 maternity beds and 6.9 cardiac beds. We were going to make $212.7 or almost $213 a day. With this solution, we're only making $210 a day, but this is still better than we would have made if we just put in 2 maternity beds and 6 cardiac beds. So we're still doing better as far as the integer solution is better than just the one that we would have rounded down with. But it will always be less than what you could have done with a true linear programming solution. So we'll see other examples in the lecture of where we have to constrain variables to be integers, and we'll actually look at examples of using binary variables. So that's it for Lab Workshop 3 Part 2.